So here is a diagram of the electromagnetic spectrum. In the center, we see visible light. What we've got here is, it's kind of like a number line, almost, isn't it? Here we have 10 to the 5th. This is measuring wavelength in meters. 10 to the 5th meters is a very long distance. 1,000 meters, that's a kilometer, so that's about a mile. That's the wavelength of some radio waves. From crest to crest, a mile. That's really, really long. And we get shorter and shorter and shorter and shorter. And then over here, for the highest energy things, this is 10 to the minus 15th meters. That's mind-bogglingly small. So that's what we're looking at, is wavelength getting smaller. And so they've got this lovely little picture here to help us understand. So in the center, we've got visible light. And visible light goes from red up to violet. And there's always a particular order. I forgot to tell the Tulare people about this. It's red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. A rainbow always has the colors in the same order. That's why when a child draws a rainbow and you look at it, you're like, what is wrong with that rainbow? It's because they didn't put the colors in the right order. And yes, it's an arch, and yes, it has all these different colors in it, but when they're not in the right order, we recognize, at least subconsciously, there's something wrong, because rainbows are always in the same order. Roy G. Biv. And they are in that order because the water acts like a prism, and it separates them by wavelength. So violet light has a wavelength of 400 nanometers, and red light has a wavelength of 750. So this is longer. And then if we go towards shorter wavelengths, which would be higher energy, we get to ultraviolet and X-rays and gamma rays. We're going to talk about each of these in just a minute. If we go to longer wavelengths, this is going to be lower energy. We get infrared, microwaves, and radio waves. Gamma rays are the shortest, have the shortest wavelength, and they're the most energetic. Gamma rays are produced by the sun and the stars. The sun and the stars are nuclear infernos. There's a great music group called They Might Be Giants. And they've done a bunch of videos, and they've done some really cool science-related songs, along with their other just kind of off-the-wall stuff. But they say the sun is a mass of incandescent gas, a gigantic nuclear inferno, where hydrogen is turned into helium at temperatures of millions of degrees. It's just awesome. But there's nuclear reactions occurring on the sun. The sun is a star. Other stars also have nuclear reactions. That's where all the light and the energy is coming from. So there's gamma rays being given off from the sun, and certain unstable nuclei on Earth also give off gamma rays. X-rays have less energy, slightly longer wavelengths, but they do have enough energy to pass through many solid substances. And so they're used in imaging, to see if you have a broken bone. They're going to pass through your bones not as well as through the rest of your tissue, and so they can give a picture of the insides of you. So both X-rays and gamma rays have uses in medicine. They're useful for imaging, they're useful for destroying tumors, but they also damage biological molecules, so they can be pretty dangerous. What has been pretty much standard way of destroying a tumor with radiation is to send beams of radiation, and this is not, yellow light beams, this is X-rays or gamma rays, very high energy, and focus multiple beams on the tumor. The problem with, using the radiation in your body is that as it goes through the tissue above the tumor, it's going to damage that tissue as well. By focusing multiple beams on the tumor, you can have these in each beam be less intense and cause less damage to the healthy tissue, but because they're all focused on one tumor, then the cumulative effect on the tumor is to kill it. Ultraviolet or UV light, that's the component of sunlight that gives you a sunburn or a suntan, depending on how long you've been out there and what your skin's like. It's less energetic than X-rays, but still has enough energy that it can damage your skin. If you've ever gotten a bad sunburn, you know, yeah, just the light from the sun can really damage your skin. Then we have visible light. Visible light doesn't damage biological molecules. It's interesting to read about how we see. What is vision? Our eyes are sensitive to light, but how? Well, the light actually causes a rearrangement in certain molecules in our eyes, and then that sends a signal to our brain. And our brain has learned to interpret these signals and process them so that we see. Very interesting to think about that. Infrared light is lower in energy than visible light, and infrared is that heat that you feel when you place your hand near a hot object. When we used the crucibles last week, I warned you, don't touch the crucibles and burn your fingers. Just put your hand near them first. If you feel heat being given off still, don't touch it yet, right? Because that would be dumb. And thankfully, I don't think anybody burned themselves. So you were good at listening about that. But that heat that's being given off is electromagnetic radiation. We can't see it with our eyes because our eyes are not sensitive to wavelengths of that range. But all warm objects, including human bodies, emit infrared light. We are warmer than our surroundings, and we are constantly losing heat to our surroundings. And so you can see that if you have the right kind of a sensor. So we have infrared cameras that can pick up the infrared radiation that's being given off. So here's a picture of a guy with some of his dogs. Normal photograph. And here is a similar picture, but with an infrared camera. And we see where his skin is exposed, that we see red around the dog's eyes and ears and mouth, we see red. Notice the dog's blue nose. Dogs have cold noses, right? The dog's nose is cold. So this is what infrared night vision is doing. It's looking for infrared light. We can't see that in the dark. It could be a completely black, dark room. The infrared radiation, though, is always being given off from your body because there's heat being lost from your body. And all you need is the right kind of a sensor to pick that up, and then you can see in pitch black. Pretty cool. Microwaves. Microwaves, that's the region of electromagnetic energy that's used for radar and also for microwaves. Microwave ovens in your kitchen, heating up your water to make coffee. A microwave oven works because microwaves are a particular energy that is easily absorbed, very efficiently absorbed by water. And so the microwaves in the oven cause the water molecules to vibrate more. They absorb that energy and increase their kinetic energy, which increases their temperature. And then the lowest energy, the longest wavelength are the radio waves. And these are used to transmit AM and FM radio, cell phone signals, TV, all sorts of other communications. When you look at a radio and it's got a dial on it and you see all these numbers, those numbers are the frequency of the station. And so you tune the radio by changing what frequency it's sensitive to. And each radio station has an assigned frequency to broadcast on so that they don't all overlap and jumble up together. So let's look at an example here of what you might possibly be asked to know about this. This says arrange the types of electromagnetic radiation, just these three that were given here, visible light, X-rays, and microwaves, in order of increasing wavelength, increasing frequency, and increasing energy per photon. So I'm just going to show you how I would do this without looking at an electromagnetic spectrum. So I would imagine that electromagnetic spectrum. You know what? Fine, I'm going to do it down here. I keep touching the back button. And right in the middle of it was the visible light, right? And so let's try to place the others on this spectrum from memory, okay, just relative to visible light. Let's put the higher energy over here and the lower energy over here. Are X-rays higher in energy or lower in energy than visible? Higher. So the X-rays were over here. How about the microwaves? Those were lower. And if this is high energy, then it's high frequency, right? And it got slower and slower as we went over here. So high energy is high frequency, and it's low, short wavelength. So I'm drawing this wave here where it looks slow over here, and yeah, it's all messy. And it's getting faster and faster in terms of going up and down. It's all moving at the same speed, but this is just going up and down faster. This is higher energy, and then we look at it and we see, oh, the wavelength is shorter. And if we imagine counting as this goes by, it's going to be a higher frequency. So then, now that I've drawn this picture for myself, then I'll answer these questions. So in order of increasing wavelength, which one, micro, visible, or X-ray, has the shortest wavelength? The X-rays, right? Because this is the short wavelengths over here. So X-rays, and then visible, and then microwaves. It's asking for increasing. So smallest first. How about frequency? That's going to be the opposite, right? Because a long wavelength, big wavelength, is going to be a low frequency. So I can take that one and just flip it around. So microwaves, and then visible, and then X-rays. How about energy? Which of these has the lowest energy? The microwaves. And then visible. What a mess. Sorry about that. And then X-rays. Okay? So I'm not going to quiz you on, what's the wavelength of red light or anything. I do think it's helpful to understand the trend in wavelength, frequency, and energy, and also to just list those types of radiation in order. There's not that many of them.